And we are now officially live with Dr. Penny Boston, who, and I hope I'm going to pronounce this correctly, is a speleologist. Is that correct?
That's right.
What is a speleologist?
A speleologist is really someone who does some kind of science in caves. So some people work on, what the origin of caves is geologically. Some people work on, archaeological remains, or the hydrology of these systems. And my particular area of focus is really the geomicrobiology. What are the tiny little life forms that are living in these these features, and what do they do, and how do they make a living, and what can we find out about them?
How did it come to being that you would be interested in climbing into caves? I mean, of all things to study, are you a geologist? Did you study geology? And how did you get led all the way to climbing into these dark structures?
Well, a lot of people who are speleologists started out being people who went into caves for fun and did it recreationally, and that was not my entry into the field.
Okay.
I actually published a paper in the early 90s with a couple of colleagues suggesting that the last best place to look for life on Mars would not be the surface, it would be actually the subsurface, where conditions might be different. And so that was in 1992, and we were looking for a way to actually try to test some of those ideas here on Earth. And we had contemplated drilling, but that's really expensive and really hard to do. And we were young and we didn't have the money, or the support to do that. And so we saw a television special, actually, on a really spectacular cave in New Mexico, which is where I currently live here in the United States. And there were a couple of really tantalizing things about it that they said. And one was that it was pristine, that it had actually had to be dug into purposefully. And so that said to us that perhaps what we would find in there would be less influenced by surface life forms. And then secondly, it was known to have a lot of sulfur minerals in it. And we know since the Viking era that Mars has a lot of sulfur rich materials on its surface. And then the third thing was an interview in this special with a geologist who had done some electron microscopy of some of the features, some of the cave decorations that you get. Most common ones that folks are used to hearing about are stalactites and stalagmites, but there are many, many different weird and interesting mineral forms in caves, and that he had seen what he thought were tiny little life forms that he thought were probably bacteria. So I called them up and I said, hello, you don't know us, but we're from NASA and we'd like to go into your cave. And so we were very, very naive. We had never been caving in a real wild cave, and this particular cave, Lechuguilla Cave, is famous for being one of the hardest caves in the world, and so we trained for a few hours, sort of ridiculously.
A few hours?
Yeah, and then in our naivete, we went in for 5 days.
Wow.
5 days underground, because this is a really huge system. This is over about 160 kilometers of map passage now, and even at the top,
that is huge.
Yeah, huge. And it's not a single linear system. It's like this gigantic maze. So it's sort of like this maze-like cloud of habitat. So it was way beyond us, and it nearly killed us, essentially. And the whole time I was in there, I kept thinking, I just have to live long enough to get out. I've been in really extreme environments before, polar environments and deserts and remote areas and stuff. And I thought, well, I just have to get out of here, and then I never have to do this again. But when I did get out, and the bruises were healing, and I, had an eye swelled shut with stuff that had fallen into it, and so I'm coming out, completely poorly trained, untrained, and with one eye swollen shut. Finally got out of the damn cave, and but then what I was remembering was that I had seen places that were like nothing else I had ever seen.
Wow.
Not just the geology, but actually that stuff that fell in my eye. When I got out of the cave, it healed up in about 4 hours. And just intuitively I thought, that has to be life. That has to be not just the chemistry of the stuff falling in my eye. It has to be something more. And I had seen, you know, amazing large-scale structures and amazing tiny deposits of what looked like minerals, but they were very unusual. And so I really got bitten by the bug. And you know, you asked, was I a geologist? Well, I was trained as a biologist, as a microbiologist, as an atmospheric chemist, and with a minor in geology. I was always very interested in that. And so I guess I was sort of predisposed, you know, to really be very interdisciplinary in my work. I always have been. And caves are a great place to do that, because in order to really understand what's going on in them, they're really semi-closed systems, or in some cases closed systems. And that means that all of the different sciences that you need really impinge on the questions that you're asking. So, so I was just apparently made to do this.
Well, it's funny. I mean, you know, people go for a run and they finish the half marathon. They go, never again will I ever run that distance. I've got bruises. I can't feel my legs. And then afterwards they go, but you know, there were some lovely things along the way. I enjoyed the route, and maybe I'll you know. So what is unique? Well, no, what is common amongst all the interviews I've done is that something serendipitous has taken place in each person's life that pushed them into the route that they are sitting in at the moment, or the path that they're going on at the moment, which I find fascinating. For you, it was gunk in your eye. For Charlie Bolden, you know, it was someone telling him, you can't do this because you are of a certain color. You know, every single person has got their own unique turning point that pushed them in the right direction. But when you were at school, did you want to go into learning about caves, or was this something that was, I mean, we've now heard what got you to doing what you're doing at the moment, but what made you study biology and go into that particular field?
Well, you know, I started reading science fiction when I was very little.
That's another common thread that everyone keeps talking about, Star Trek and all these things that happened.
I mean, at 6 years old, I think, I discovered Robert Heinlein's juvenile science fiction. And I was totally hooked. And then at school, we used to have in the United States in the 50s and 60s and probably into the 70s, we had these little newspapers that kids got every week called My Weekly Reader. And one particular issue had 2 articles in it. And you know, they were like little tiny articles. And 2 articles, and I was 8 years old. And I read one of the articles, and it was by Carl Sagan, the great astronomer and planetary scientist, and 1 foot in astrobiology, which we called exobiology then. And he was writing this little article for this kid's newspaper on exobiology. The idea that we were then starting to look for life beyond Earth. And in the same issue, there was a little other article by Dr. Frank Drake, who is the developer of the modern search for extraterrestrial intelligence, and he had put together this Drake equation, which we still use. And I read those 2 articles, and that was it. That was it. And even though I flirted with many sciences, I mean, I always had this this path of what is the origin and evolution of life in the universe, you know, particularly our galaxy, which I figured I could somehow reach parts of. And everything that I needed to do that, I mean, starting with the core of biology, I almost went off in the neurobiology and animal behavior direction, but there was something that kept pulling me back to life as a phenomenon on planets, and I guess I'm a natural explorer. And I come from a theatrical family, and we traveled all over the world all the time, and I think that was part of it, you know, the sociology of my growing up. And I just wanted to go explore places where I would find life forms that nobody had ever found before. And of course, as a little kid, I figured by the time I was a grown-up, meaning like 20, that we would already have the ability to, go to different planets, in my lifetime, and that it wouldn't be that hard. I mean, as I went through school, I realized that we were, unfortunately, quite away from that. And so what I chose to do was really explore extreme environments. And
Sure.
those extreme environments, I started with the high mountains and, climatic extremes, salty environments, really dry, all that stuff. And so, I was already in mid-career. I was already probably 10 years past my PhD by the time I sort of focused on the cave stuff, And I haven't totally given up surface studies. We're very interested in these rock varnishes on Earth that clearly have a microbial component. And we also are interested in the fact that those have been, seen on Mars. Whether or not they're biological there is a huge question. But at the time that I was in school, in college, and in graduate school, the whole solar system was opening to us. The Voyager missions to the outer solar system, learning that Venus was such an extreme environment that probably our kind of life could not easily live there or at all. But then that sparks ideas of, what other kind of things can be used in the universe to make life? We don't know. It's totally speculative at this point. So that was really my pathway. And I expected to be doing that until I dropped out.
Now, what doesn't surprise me, and I'm trying to find common threads when I interview all these people, is that as a STEM communicator, if I put out information, it might hook one or two people. If I don't put out the information, it's not going to hook any. So it's important to continuously expose young people to new ideas and things that might pique their interest, because that could be the origin story where they start moving across a certain path, and in the back of their mind, they're always interested in space, and look at this, you landed up now working with NASA, which is a very exciting new change. You've only recently started with NASA, or you've always been with NASA?
I did a number of different programs, summer programs with NASA when I was a graduate student, and then did a NASA postdoctoral fellowship when I got my PhD, and have not worked inside of NASA until the job that I'm about to take the end of this month. But I've been a fundee of NASA. So NASA has been one of my chief funders of my research while being at research institutions or, like I am now, a professor and chair of a department and things like that. So, and I've served on many, many NASA panels and boards and studies and working groups and all that stuff. So I've always thought of myself as sort of circum-NASA, although I've been, on the inside as a postdoc, and now, early in my career and now late in my career, I'm going back in to try to help guide the science that I love, and is really the driving passion in my life.
Well, I think it's amazing, but now, of course, we're going to get to the juicy bits. The real juicy bits are that you go into a cave, and sometimes these caves are not very hospitable. They don't say, "Come inside. We're nice and large and cavernous, and we've even trimmed the stalagmites and stalactites for you. So just come along and explore. And by the way, this is what you should be looking at." You often going into very unhospitable caves. Can you tell us about some of the unhospitable ones you've been to?
Well, part of the reason that we're going into caves is different than you go in when you want a good tourist experience, right? When you want a tourist experience, you don't want things to be life-threatening, and you don't want them to be uncomfortable, and you want to go and look at this wonderful feature of nature in a relatively comfortable set of circumstances. But our goal is really different, and that is we're really looking for life forms and their associated geochemistries and atmospheric chemistries that are really sort of pushing life up against the barriers of what it can do. So because of that, those environments are intrinsically extreme. in terms of temperature or chemistry or whatever. So we have operated at both ends of the temperature spectrum. We have done a lot of work in a cave system that has no natural openings and was actually discovered accidentally by way of mining in Chihuahua in Mexico. The temperatures there are extremely high, 40 to 60 or even 80 in some places degrees centigrade, although the areas that we went into were in the approximately 40 to 50 degrees centigrade area, and to the point where we actually had to wear suits where we were essentially packed in ice in order to survive it, and only go into the hottest places and work for 15 to 30 minutes at a time, and then have to come out and recover for 4 hours. And even though we had ice pack under our helmets, and we were packed in ice vests, and we had backpacks on with cooled air blowing across ice cylinders so that we could breathe it and not scorch our lungs. But we weren't able to cool our limbs, our arms and our legs. And so it was a very weird experience. It was not even like experiencing it as heat. It was experiencing increasing weakness in our legs and arms and increasing lack of ability to tell our body what to do. It's sort of like getting really stupid.
That is incredible.
Yeah, it reminds me of the scene in the classic movie 2001 where Hal has misbehaved himself, the supercomputer, the sentient computer, and they're turning him off. And it's this very moving scene where you sort of see pieces of his intellect dropping away, and he knows that. And I've always thought that was a great tragic scene, and so that connected in my mind with this experience. You can feel your mentality going, and then it's time to get out. And I did actually stay in too long once and really take a big hit. We were in for 50 minutes trying to get something to work, because we were trying to look for life forms buried within these crystals that we believed had been in there for tens of thousands of years, and we had reason to believe that they were still alive, and so we were trying to get those out. And so we pushed and pushed and pushed, and it was too much. So that's the real hot end of the spectrum. And then the cold end of the spectrum.
Yeah, okay.
So we've been doing some new work in Mount Rainier, which is a big volcanic mountain, but it is an alpine system in the state of Washington in the United States, which is the very northwest corner of the United States. And it's very cold up there, and because it's a volcanic system that is relatively recent, it still has a lot of fumaroles and gases coming off it. So it has a poisonous gas component that we're interested in and have studied in other caves, but it also has this very low temperature. So it's about -3 degrees, and these are caves that are formed in ice masses. So they're essentially glacier caves that are formed in ice masses because of the thermal emissions from these fumaroles. So we think that these are very interesting because they are potentially relevant to life on icy bodies like Europa that orbits around Jupiter, or Enceladus that orbits around Saturn. So it's yet another endpoint in the spectrum of temperature, and it also has the gases. And then we study a cave in Tabasco in Mexico, the other side of Mexico from the hot crystal caves, and there we have a cave that is absolutely dripping in sulfuric acid. And this is because a large amount of the hydrogen sulfide gas is coming into the cave from deep sources, and that goes into solution in the water and complexes with the oxygen there and produces sulfuric acid. And so there we have this very poisonous gas environment and in the fluid there. So we've done work in there for going on, I guess, 18 years now. We have worked in caves that have a lot of CO2 coming into them and found organisms that specialize in making their living in those circumstances. We have gone into caves that are so difficult and so tiny that you're essentially crawling all the way. on your belly or on your back with your helmet off, and trying to get into these areas to really look at these organisms. And more, okay? So the point is really not reality TV where we're just doing this for the sake of it. The point is really to get in there and find organisms that are dealing with circumstances that are extreme here, but actually might be more average circumstances in other habitats on
other planets. Correct.
Yeah.
Wow.
What happens if you have a planet somewhere, maybe not even in our solar system, maybe thinking, as we're entering the era where exoplanets are now beginning to be able to be analyzed for real, not just detection, but beginning to be able to tell things about their atmospheres and their thermal properties and so forth. So, we're sort of practicing for not just our solar system, but even beyond. So, trying to scope out what carbon-based, water solvent-based life like us can do, far beyond our capabilities as humans, but not far beyond the capabilities of the kind of life that we represent. Microbes.
Wow. I mean, I'm just thinking now that, you mentioned that you had caves where there were crystals that were very, very old, several million years old, and you were
500,000 years old, yeah.
500,000 years old, and you expected to still find life inside them.
Well,
why would it last so long?
Yeah, we thought it was a possibility. In the literature, the scientific literature, and in science fiction too, people have speculated about whether or not life could persist in some kind of dormant form for a long time. There are ideas of panspermia out there, which means, can organisms go from one body in a solar system to another, or an even more extreme form of it, can they be ejected from one solar system and eventually end up in another solar system? Can life even survive unbelievable cataclysmic events like supernovae or things like that? We don't know the answer to any of these questions, but those ideas are out there, and so trying to test those ideas where possible. And a lot of other folks have gotten into that game and found what they believed were life forms that have been trapped in things like ice or salt. So salt forms a lot of little pockets within the crystal structures, big salt masses. You get what are called fluid inclusions, which means little pockets, little holes, little defects in the crystals that contain fluids. Sometimes they contain gases as well. Sometimes they contain solid material. And we knew that the giant crystals in this Nika system in Mexico had examples that we had seen courtesy of a collaborator and friend of ours, who's one of the world's great cave mineralogists, Paolo Forti in Italy. And he had done some exploration of this system, and he had sent some images to me of what he believed were fossil microorganisms within these inclusions. And so I thought, well worth looking at. I mean, we're very interested in the fossil life as well. But maybe we could even find some DNA, in these inclusions that might still be sequenceable. So there are a lot of questions and a lot of claims that people have had about, the oldest ones that I know that have been claimed are in salt deposits that we actually have here in New Mexico, in the southern part of New Mexico. And an investigator named Russ Vreeland, a number of years ago, claimed that he was able to reawaken organisms that had been trapped for several 100 million years. Okay, so that's way older than what we're claiming. But we think that the organisms that we were accessing are probably on the order of 50,000 years of being trapped within these fluid inclusions. And the kind of mineral that we're looking into, which is a type of gypsum, it's a type of gypsum, crystalline gypsum, which is not a very exotic mineral. It's, the wallboard in the room that you're sitting in probably is made out of it. and me here too. But that is much less questionable than salt or ice because it's a brittle mineral and it doesn't flow plastically over time. So we're pretty sure that these guys that have been in there that we were able to reawaken have indeed been trapped for on the order of 50,000 years. We're not claiming hundreds of millions, but nevertheless, this is another piece in this puzzle of how long can organisms last in geological materials. Is it even plausible to claim that they could survive within geological materials that either would get blasted off a planet, for example, Mars? We know that we have Mars meteorites that have come here to Earth that we're studying, or not. So it's just another little piece in this gigantic puzzle to answer these questions eventually.
Wow. Well, I noticed that Mr. McNulty's class have joined us as well, and hopefully they're going to be asking some questions. We interviewed Carrie. Hi.
Hey.
And we've got Dondi, who's joined us from Hungary as well. We interviewed Carrie Corrigan, who obviously looks at meteorites, and she's been looking after the Martian meteorites, and she also did mention that they'd be looking inside to see if there were evidence of some form of life or microbe. So if you were going to be taking all the science that you know, and we now know that they are planning to go to Mars, what should they be looking for, and where are they going to find it?
Well, I'm a partisan of caves, not just because I study them, but the reason I study them is because they provide such a different set of environments from the surface. And the current surface of Mars is a pretty darn inhospitable place. It is a planet that probably has somewhat nicer seasons, and we are not in one of those on a very long time scale. So I think that, while it's valuable for us to continue to look for evidence of life on the surface, I really think if anybody is alive there, it's going to be below the surface. Now, how far below the surface? We have many potential plans for drilling. Upcoming missions, both NASA and European Space Agency and some of the other spacefaring nations, are very interested in drilling. But at this point, the amount of drilling we can do is not very deep. It's a very gigantic technical issue about how to do that. We have been working on the idea of accessing the caves that we know exist on Mars. So I've been writing...
Are there lots of caves?
Yeah. I've been writing about it for 20 years as almost an article of faith in advance. And it wasn't until really about 2004 when I published a little article sort of detailing what you would find and the fact that we were pretty sure we were seeing volcanic caves in some of the images that we had already received from various Mars missions. And in 2007, with the fabulous resolution of the HiRISE camera, some colleagues, Glenn Cushing and Tim Titus and Jet Wynn at the U.S. Geological Survey in Arizona published a paper showing 7 different pit craters, these big shafts into the subsurface. And then, ever since that, the hunt had been on. And we had a specialty meeting last fall to consider extraterrestrial caves of all different kinds and all different bodies. And the consensus of the group then was that there are at least 2,000 cave features already identified on Mars. So we think that based on our studies here, based on some theoretical work that's been done by other folks about what you could expect for the habitats that might be available, even in these relatively shallow lava tube caves, as they're called, or pit craters caves, that they would present a somewhat more benign environment, including protection against ionizing radiation, which, is a hard thing to do. Rock is pretty good at it. And so, that's one possibility. Another possibility, of course, is looking for deeper caves. But here again, we have significant technological challenges in accessing that. I work with several different robotics groups over the years and have a current collaboration with a roboticist in his team, Aaron Parness at the Jet Propulsion Lab in California, and he has developed this system of climbing robots that we are now testing here in caves on Earth that rely on a whole series of like fishhook-like spines. And when the robot puts her pad down on a rock surface and kind of withdraws, some proportion of those spines hook into the rock. And so, you know, we and others are working on how we can actually eventually get access to those kinds of environments.
Wow.
In the meantime, of course, we have lots of missions planned, both within the United States and with our international collaborators, you know, to try to continue to look for any kind of evidence on the surface, certainly particularly of extinct life. So geochemical traces, actual physical microfossils. I don't personally expect us to find any large-scale fossils, but you never know. You know, if we could figure all this stuff out from first principles, we'd already know everything. So
That's true.
a lot to do, a lot on our plate.
So, I mean, if I was going to take a trip to Mars, which we're planning in the 2030s, and I get there and I start digging, what sort of creatures or microbes or things would I actually find if there was something to find?
Well,
and why is it such a big deal?
I recommend that you find a cave.
Uh-huh.
And hopefully by then we'll have space suits that are cave-worthy. And I would suggest that you take yourself into that cave and sample particularly fine material, but also look for unusual patterns. One of the things that we are interested in is what my friend Diana Northup, friend and colleague Diana Northup, calls microbes masquerading as minerals. A lot of the microorganisms on this planet that are the type that we think could potentially live in such an extraterrestrial environment or have lived in such an extraterrestrial environment and left a beautiful signal for us, a love letter, if you will, a biosignature pattern on the walls or on the ceilings, or unusual minerals that are only produced when life is present. There's an entire huge array of those biominerals. Sometimes those minerals would be made anyway, but not in the same way. Sometimes the evidence is morphological, that is, physical. You can sort of see entombed microorganisms in minerals, and sometimes it's just the chemistry of the mineral itself that is actually altered by the presence of life. And this is true on Earth. Okay, this is not just somewhere else. I think the more we work, the more we understand that the subsurface of Earth down to at least 5 kilometers and maybe 10 is profoundly affected by the presence of microorganisms. Even in South Africa, where you are, I mean, a lot of the most magnificent finds have come from deep gold mines there, where human access to 4 kilometers and counting, the deepest we can actually send investigators, has shown just remarkable organisms that are living off radioactively split hydrogen and oxygen from water molecules. And then the organisms at those depths in South Africa are living off that hydrogen. I mean, they are very crafty beasts. They find a way to get...
I've heard so. I've heard so.
So that
is incredible. I mean, I'm always just blown away by the fact that, yes, we are looking to go to another planet and we are expecting to find life, and most people have got expectations of little green figures running around. The reality is that it's going to be some sort of microbe, but not even an insect. We're talking the most primitive, basic life forms. But so what? So what if we find these things? What is the big deal?
Yeah, and I think that, we don't know yet. I mean, one of the things that I think is an eye-opener, those systems that I was just talking about in South Africa, there's tiny little worms that are now living off the bacteria that are the base of the food chain there. So, you know, I'm expecting and planning for microbial life because that's the most likely. But I wouldn't rule out tiny higher life forms until we actually do the work. Because one of the things that I have learned that is really deeply embedded in my heart and my mind, and that is, no matter how much we think this through from first principles, based on the knowledge that we have here, there are surprises. And I have been lucky to find a lot of those surprises, and so have others. And, you know, every time we decide to think that we really know the bounds of what we're looking at, some aspect of life will surprise us. So, you know, we know that on this planet we have these incredibly tough little, very highly evolved little guys called tardigrades. I saw some question, flip
Yes.
5 tardigrade, and
Carl was asking questions about that.
We're gonna you know, those little guys. Whether or not an extreme environment on a planet can give rise to those organisms, or whether or not you have to have a more benign planet like ours where you have the rise of more advanced life, and then it learns to re-invade the extreme environments. I don't know, and I don't think anybody knows. It's at this point, it's completely speculation.
Okay. And Carl also wants to know, in your opinion, which planet or moon in our solar system, if you had to draw up a hit list of where you think we're most likely to find some sort of life form, where do you think it's going to be, besides Mars?
Well, I'm super jazzed about Enceladus.
Oh, why?
Because Enceladus is actually holding up a big neon sign that says, I got organic material in here, and it's spewing this stuff out. So, I think she's soliciting input. I think she's getting us to go send a mission. And the kind of mission that we can send to actually look at that material is probably easier than a deep sub-ice mission to something like Europa. Now, of course, Europa is a fabulous destination. We're tremendously interested in it in the community. You know, the Mount Rainier work that I discussed earlier directly pertains to that, and work that we and other colleagues and some of our students here, where I'm a professor, you know, have been doing in Antarctica or in the Arctic. All of those are preparing us to look at both Enceladus and Europa, maybe even Ganymede. But Europa has a lot of technical challenges. We can send missions to look at the material on the surface. And because the moon is very tectonically active and cracking on relatively short geological timescales, there's the potential for material from the interior liquid contents to actually be brought up onto the surface by geological processes. We don't know what the timescales are, so we don't know how fresh that material would be. We do know that the radiation environment of Jupiter itself is very extreme, so any material on the surface of Europa will have been bathed in that. So, you know, this is not going to be an easy set of missions, but Enceladus and Europa are way up there on the hit list. But I have been struck by, you know, every time we go to another body, they turn out to be much more fascinating than we thought. And even things like these magnificent images and science coming back from Pluto. Well, Pluto's a pretty different place, but I would have thought that Pluto was a little dead ice ball out on the, you know, edges of the solar system.
But the photos showed a completely different experience altogether.
It's geologically active as we speak, you know. I mean, what does this mean? We're all puzzling over, where is the energy coming from? You know, it's way far from the sun. Does it have a radioactive core? What's driving Pluto? Information that we've gotten about Ceres, for example, and other big asteroids or minor planets, those are much more geologically active than we could have guessed. So, you know, I think that all the pickup sticks have been thrown into the air again. And we really have to focus on trying to analyze these things from first principles, which is really hard to do. And then what I do and other colleagues do, and that is to try to find places on Earth that we can directly study that have at least some aspects in common with these bodies.
Wow. Well, I know that we had a question from Mr. McNulty's class. Where's Pat? You want to ask your question? Come on up, Pat.
Hi.
Hi.
Go ahead, Dad. Yeah.
How long does it take to get to Mars?
That depends. So Mars is a planet with a much less circular orbit than we have. We have a fairly circular orbit. Our planet does. But Mars has a more of an elliptical orbit. So sometimes Mars is effectively closer to us, and sometimes it's further away. So with our current methods of propulsion, about the very best we can do is on the order of 8 or 9 months for a really quick trip. But if you have a less favorable situation where Earth and Mars are farthest away, then you're probably looking at a 2-year trip time. So you got to pick your target dates for when you want to launch very cleverly, and also hope that the folks that are working on better ways to actually drive our rocket ships to Mars will improve. And so some people are working on what are known as advanced propulsion systems to try to enable us to get to planets like Mars a little bit faster, maybe a lot faster.
That's a good question. But now, of course, you've opened up a can of worms, because now they've got a whole bunch of questions. We have Pat, no, not Pat, we had Maddie, who wants to know what made you want to do this job. And I think we kind of covered a little bit, but maybe you want to explore a little bit further. And then Becca wants to know, how much can you earn doing a job like this? Is it really a lucrative job choice? So maybe we want to just get Maddie to clarify what the question was about. Maddie, why don't you come up and ask the question yourself?
Well, I was wondering what made you want to have this job, and when were you hired to work for NASA?
Well, I was saying earlier, and maybe you guys didn't tune in quite early enough to hear it. Actually, when I was a really little kid, at about 6 years old, I started reading science fiction. And then when I was about 8, I read a couple of little articles about what was then called exobiology, which meant, what I do now, which is sort of thinking about how we would look for life on other planets, and how we would maybe also look for intelligent life that we could communicate with, and that really got my attention. So when I was in school, I studied all different kinds of sciences, and when I was a graduate student, after I had finished college and went on for more training, that's when I really started doing it professionally. So I did several different summer programs as a graduate student at NASA centers. I worked on various different things. And then when I was finished with my doctoral degree, I did 2 years at a NASA center. And then I went into a research center and did research, and then went into a position as a university professor and department chair. So I've done a lot of different things in my life, and always followed this pathway because I really love to explore. But part of what you pay for exploration is not just the fun of doing the exploration, it's doing the science and the hard work that you need to put in to actually make sense of what you're seeing. There's a difference between doing something for fun on vacation and going somewhere where you're doing a camping trip, and that's wonderful. The difference between that and the kind of stuff I do is that when I go on a trip, I'm actually working, and I'm taking data, and I'm taking samples, and then I haul all that stuff back to my labs and my office, and I work on it for probably thousands of hours for every hour that I'm actually in the field. So, it's a true occupation. There was another question about how much...
Another question? Yes, let's see who it was that asked it. I think it was Becca. Becca, where are you? Come on up, let's hear your question.
How much do you get paid?
That's a big question.
That's a big question. I've gotten paid all sorts of different things.
So, I mean, is it in general for the career that you're in? Is it a good career?
Mm-hmm. It's a good career. If I had wanted to become fabulously wealthy, which never interested me even a tiny bit, I would have gone into something else. It's not a field in which you typically become extraordinarily wealthy unless, I guess, if you want to pursue science to develop products like biotechnology or something like that. But that's not something I'm particularly interested in. I just want to have a comfortable living and pay my bills and not have problems with that. So it's been very satisfactory to me on that end of things.
So I think, Becca, what Penny was really saying is that if you were looking to retire on doing a couple of hours work in this field, it's probably not the field you're going to choose, but you would do it for the love of it anyway. That's why you would do it, not really for the money, which I think is pretty much like that. Now, I know that Mr. McNulty says his class has to go, so we're going to wave and say goodbye to Mr. McNulty.
Thank you.
Bye-bye, bye-bye. So now, of course, it's just us two now, but we've still got viewers who are watching it live on YouTube or on the Living Maths website. With the Humans to Mars Summit coming up, Mars is obviously very exciting. There have been movies and books written about it, but in particular, Mars is getting a lot of attention. They're talking about sending all these astronauts. Is there something that you've been holding back? Is there something that we should know, maybe about the planned missions that are going there, that would be quite exciting for people to know?
Well, I mean, I've spent my entire career not only doing the work that we've already discussed, but I'm a very strong proponent and have always been since I was a little kid of human missions. And I never personally wanted to be an astronaut, but I really believe in the importance of us as a species exploring our environment. And as we come into the space age in the middle of last century, we began to really have the potential to really explore. So at this point, we've only ever been to the moon with actual humans. And that's something that we have not done for a long time. But people are working back up to the idea that we'll go do that again. And we're planning for the potential for sending a human mission to an asteroid. And we are continuing to plan for human missions to Mars. And I think that's tremendously exciting. Are
you involved with the OSIRIS-REx mission?
No, I'm not. I'm a fan. So I say,
you are a fan.
Oh, OSIRIS-REx.
So I mean, that would be also a potential to find microbes and bring samples back to Earth.
One of the things that I think is really important, as much as I love robotics and have a great deal of faith in robotic development as we go forward, I know that the fluidity and the intuitive abilities of a well-trained field scientist are far in excess of what we can expect anytime soon for artificial intelligence. I know that there are wonderful developments in that, but we are pattern recognition, thinking, and synthesis machines, our brains are, that have been refined by literally billions of years of evolution. We're very good at what we do, and what we do is naturally and subconsciously interrogate the environment in a way that is hard to match. And then we have all of this training which allows us to take these innate biological abilities that we have and translate that into understandable science. And that is a combination that I think nothing but a human currently offers. And so all of the difficulties that come with trying to take our relatively fragile structures and prepare them for working and studying and operating in an extreme environment are worth it. And I don't view this as robots versus humans kind of thing. I think that we will essentially grow together, and that one of the amazing talents that humans have is the ability to accept tools intellectually as self, if that makes sense. That we, when we pick up a pencil, we don't cognitively think, oh, I'm picking up a pencil and I'm using the pencil. I mean, we absorb tool into ourself and we operate that way. And I think my great hope is that our robotic assistants and collaborators, if you will, into the future will be able to work with us on that basis.
But
and
now
solve some of
on
the problems.
On Mars, they actually have a very sophisticated sampler of soil, and the rovers are able to take samples and test them and do very sophisticated testing, if I'm not correct.
Yes.
So obviously that would be the goal, to develop far more sophisticated equipment that could go down, test the soils or whatever, and send them back. But obviously, if we have human beings doing it, then they would have to be set up in a lab. But now, what happens if they bring back microbes? And there's, you watch all these science fiction movies. It's bringing back a foreign or an alien species to our planet. Is there a danger in that? That maybe it'll thrive on our planet that it couldn't do on Mars, and then it becomes a problem.
Well, there is a 60, maybe 70-year heritage of worrying about all of those issues. It's not something that we're just worrying about now. So very early on in the space age, people began to worry about what's called the planetary protection issue. And there are two aspects to the planetary protection issue. One is what's often been called forward contamination. So we don't want to muck up another planet with organisms before we've had a chance to study it. And we don't want to adversely affect any alien biosphere by importing something that would be harmful. So that's one area of concern. And then the other area of concern is what's known as backward contamination, which is the idea that, of course, as we explore and we eventually take samples from a body like Mars that may have a biological potential, and then we bring those back to Earth, how do we make sure that we don't harm our one and only home planet? And so both of those are governed by a lot of things. We have an international treaty, the 1968 Treaty on Outer Space. It's got a very long title, as legal things tend to do. And the planetary protection issues were encoded legally in that. So all of the signatories to that treaty are bound by those basic principles of not harming other biospheres and not harming our home planet. Now, that's legal language. There has been a whole lot of continuous refinement of those ideas and how they get implemented through an organization called COSPAR, which is an international body that deals with all things space, and planetary protection has a big part of that. NASA has a planetary protection officer. Dr. Cassie Conley is the person currently holding that office, and it is the job of her office, and in fact NASA as a whole, to make sure that NASA adheres to those principles and best practices as we currently understand them at any given mission, when sending missions to different bodies, and particularly when sending missions to bodies that from which we may be returning samples, and Mars is one of those. And we constantly work on this issue. There are numbers of people who work on aspects of what can Earth life tolerate, what are the chances of contamination, where on Mars do we have what are called special regions. This is a a formal designation, that we may have to exercise extra caution when we send missions to them. I think we're greatly in need of revamping some of our technologies about how we actually do the engineering to send some devices to these other planets. I think that's something that we can work on. It's something that's really one of my goals to help with when I go back into NASA at the end of this month. And so it's a big deal for us. I have served on the NASA Planetary Protection Subcommittee that deals with these issues for the last 8 or 9 years, you know. And I fold it into all of my thinking. I think it's something that we can do successfully. And I think it's something that we can do successfully with robotic missions, and have been doing fairly successfully with robotic missions. And I think it's something that we can do even with future human missions. I think it's not a showstopper, but we have to get smarter about it. And it's something we ought to do, we have to do, we're legally, internationally obligated to do, and it's really important. And it's important that we continually share information and this commitment to these goals with our international partners around the world in other spacefaring nations. And in fact, as we go into the era of what people are calling new space or private space, where we may see individual organizations that are not attached to some country in particular, they also are bound by this international treaty apparatus. And even though they may be independent companies of one sort or another, it's very important that they adhere to these guidelines, partly because they owe it to the rest of humanity for all the reasons that we've stated, but also partly because the actual value of the science of life detection really hinges on our being able to control contamination. So it's a very big, huge field, and I'm just giving you a taste of the answer.
Mm-hmm. I mean, are you looking within the next decade or the next 5 years to do an "I told you so" speech, where I knew they were going to find this particular thing, and in fact I wrote about it 20 years ago? Do you feel that you're going to have one of those moments?
I don't know. I mean, I sure hope so. I've been working my entire life and you know, thinking and planning for this my whole life since I was a small child, really. And now I wouldn't say I'm quite an old lady, but I'm getting in that direction. But I think that having a goal keeps you young. So I'm sort of thinking that I'm not going to toddle off the stage and drop dead until we actually do find evidence. So in that sense, maybe it's kind of an insurance policy.
I like that. I like that. That is very good. Well, we've only got about a minute left. Is there any advice that you would like to give young people to either get into the field that you are in, or lessons that you've learned that you would like to pass on to them?
You know, one of the lessons that I've learned is that you get a lot of advice from people when you're young, and probably 90% of it is nonsense, and you should follow your passions. And
so you're telling me that the advice you're giving now is nonsense, and people must just follow their passions? I like that.
Point, yes. I mean, you know, within realistic levels, I guess, you know, there's some careers like maybe who knows what that are pretty unrealistic. But if you think you have the ability to follow your interests, then I would be pretty single-minded about that, even in spite of conservative advice of your elders or your parents or whatever, that you should actually go be an accountant. You know, if you don't want to be an accountant, then go off and give it a try. You know, you can always change your mind, right? It's not a one-way path. It's not like you decide that you want to do something and you're stuck with it forever. I mean, I probably have glued together 6 or 7 careers by now.
Wow.
You should never be afraid to go off in a different direction if you think that's where, you know, something meaningful to you lay.
Awesome. Well, thank you so much for giving up of your time. I know that you are a very busy person, and we appreciate the fact that you spent time and answered some of the questions of the students and some of our colleagues. This will obviously be broadcast on our website, and then the video is going to be played continuously throughout the Humans to Mars Summit, so that young people can connect and watch. I'm going to stop the broadcast over here.